Thank you very much, Markus, for the kind introduction. And good afternoon to everyone. I'm truly sorry to have interrupted this lively poster session. I think it was a very interesting one, and I'm truly sorry that I now jump in with this boring talk here. But nevertheless, there might be a message also for you. Let me start by explaining what we do at the Chair of Systems Design. So we can be best characterized by doing data-driven modeling. That's a bit beyond data analysis. We took what we learned from the data analysis to put it into agent-based models. And at the end, we have fulfilled our aims. We have an agent-based model that reproduces what we have seen in the data before. We are interested in economic networks and social organizations. Here on the left-hand side, you see an ownership network. There are millions of firms, and firm A owns a part of firm B, and firm B owns a part of firm C. So there is a global network of ownership. And if we condense this down to the very core, then we see this: 1,360 firms that mutually own each other. And they basically contain a revenue of 20% of all of the firms of the whole world, right? That's an interesting insight for the regulator. If you want to regulate the economy, then you have to think of this picture, right? On the right-hand side, we see a different example, a community of small bats, Bechstein bats. They are of about this size. They have a brain of 10 grams, and they can remember their friends for 20 years. So we have investigated how their social network looked like, and this is one example. But today I talk about a very different topic, namely I talk about collective emotions. And first I want to introduce the topic a little bit by quantifying emotions, then we look into how we model and measure cyber emotions, and then we hopefully also talk about a few applications. What drives our behavior? That's a question that is pertinent to all of the social sciences. And if you think of economics, for example, then there is this concept of rational agents that calculate their utility and then they make a decision. But this already raises the problem: where do these agents have the perfect knowledge from to calculate their utility? And how did they quantify their utility at all? In addition to these conceptual problems, there are other ingredients that influence the decisions and the behavior of these agents as much as the utility, namely the social ingredients. If we look at the individual level, then we see that trust or distrust plays a role, that empathy or aggression plays a role in the behavior and in the decision. On the collective level, it's the same. We have herding effects, we have group feelings, and at the end, we also have collective emotions. And the question is, how does this impact our behavior as social individuals? I will focus only on emotions today, and first of all, I should explain what emotions are. So, this slide says emotions are short-lived psychological states that consume individuals' energy and strongly bias their behavior. That means emotions are not what we think they are in terms of mood, for example. If you look on the top of the slide, then you see a timeline on logarithmic scale. On the left-hand side, there are very short-lived states. On the right-hand side, there are the lifetime. There's a lifetime behavior, and emotions are right here in the middle, which is called core effect. They last between seconds and at most 1 to 2 minutes. If they last for a day, then we don't talk about emotions anymore. Then we talk about mood, for example. And if it lasts even longer, then we talk about personality traits. So then, if we think of emotion as short-lived psychological states, how do we quantify them? We use a model that was introduced by Russell already in 1980, and this model quantifies emotions along 2 dimensions. One dimension is called valence, that describes the pleasure that is associated with an emotion. And the other dimension is called arousal, that describes the kind of activity that is induced by the emotion. And we put them together here in this kind of polar diagram, and then you see that surprise, for example, is an emotion that has a very high level of arousal, but only a medium level of valence, for example. And if we want to map all of the emotions in this diagram, we can do so. Then it looks like this, right? So you see there are very many emotions, and each of them has a specific place in this polar diagram in terms of valence and arousal, even that I don't spend time on reading this. Talking about emotions resembles maybe a little bit of pleasure and happiness. So what do colleagues do? For example, James Fowler and Nicola Christakis, they did a study about happiness. But that's a very, very different thing. They compared for a village in Maine the reported happiness of people over a very long time frame, in particular 20 years, and then they compared how these people felt in a survey that was taken every year, and they tried to understand whether happiness is some sort of contagious behavior. Of course, if we talk about processes over such a long time scale where we only have very little measurements, then we cannot really verify whether happiness is contagious or not. At least these kind of studies are not what I have in mind when I talk about emotions. Remember, we talk about short-lived states. The following, after having explained how we quantify emotions in terms of this polar diagram, I look into how we get these numbers. So we look into online data mostly, and every one of you who uses an online social medium, for example a chat room, then knows how it goes. You write something, you see what other people write, and so forth. And we have the streams of all of this. You see on the left-hand side, we marked all the words that have a negative emotion in red, and on the right-hand side, we marked all the words that have a positive emotion in green. And then we analyze this text by means of a technique that's called sentiment analysis. That's nowadays a standard tool in computer science. I come to this in a moment. Additionally, we also monitor the people when they write this text. And then we can compare what they write and do the sentiment analysis of the written text. Or we can also measure how they feel in terms of their physiological response when they read and write this text. And then we can put these two sides together to understand the individual generation and response of to emotions. So let me shortly describe this sentiment analysis. So there are two classic ways of doing this. The first one is the annotated lexicon. There's a lexicon, a new lexicon, that's the proper name of it, where psychologists have chosen a number of words and then by means of surveys have found out how people, what kind of emotions people associate with these words. I'll give you an example afterward. And the second technique is the supervised learning. So we have a text and then we have some annotation for the text. We have a short training set that we use to train the classifier, and then later we use this classifier to basically analyze this whole text with respect to emotional polarity, for example, or to valence and arousal. So let me start with one example of the survey-based lexicon. I took a slide here from Peter Dodds because I like this so much. So he analyzed a text of the song Billie Jean by Michael Jackson. And here you understand how it works. So they go through the text, then they mark every word that they find in this ANU lexicon, and then they write down how often this word appears in the text. So that's in the middle part of the slide. And then they also look into this lexicon and find out what is the associated valence for this word. So valence was the pleasure that I have by the emotional pleasure that I have from this term. And then they simply calculate the average valence of this text by multiplying the valence of each word with the frequency and divides this by the mean number of words. And then they get something like the average valence of Billie Jean is 7.1. And if we want to compare this with Thriller, then that was 6.3. And the average Michael Jackson is 6.4. So what does this tell us, right? So that's the problem. In fact, there are 3 problems that are associated with this kind of analysis. The first problem is associated with the performance of the algorithm. We implicitly assume that emotion is coded in a word, right? So that means the context sensitivity of the whole expression is a tricky issue here. The second thing that you can also immediately get is sometimes there is a subtle meaning that has then a different emotion than what we really say in terms of word. For example, that's not bad, right? So then the question is how good it is. Or what was the other example that John Bollen used? I sell my love for money, right? Money and love have a very high positive valence. So that means that's a sentence with a very high valence value, but in fact it says something negative. Right? Okay. The second problem is the quality of the lexicon. I mean, these are handmade surveys by real people with real people. That means that the human ratings that we get for this lexicon are not for a tremendously large lexicon. So if you go for the English ANU lexicon, it has only 1,000 words. The German is a bit larger, and the Spanish has about the same size as the English one. So that means we can only sample these 1,000 words. So the situation has changed recently, this year, by an improved lexicon. But more or less, most people still use this one. And the third problem is related to the meaning of these numbers. In order to find out whether 6.5 is incredibly good or bad, we have to know how emotionally charged our everyday language is. So what's the reference point of having such a number, right? And this is what we first have to find out. So we ourselves did a large-scale analysis of exactly this problem. We used these 3 lexica that I mentioned for English, German, and Spanish. And we looked into the valence distribution of these lexica. That's shown on the first row of this graph. And you hopefully see there is one line that's approximately at 0. That's the mean value. So that means the psychologists did a very good job in creating a lexicon which is, on average, emotionally neutral. So they have balanced all the words in this lexicon in such a way. So that's a good thing. The question then is, how often do we use all these words? Some words are used more often than others. In order to find out how often a word is really used, we use the Google Ngram dataset that basically contains all the words used in the internet. And then we calculated from this Ngram dataset the frequency at which all these words are used, and then multiply this by the respective valence. And then, if you look into the second row of this graph, then you see that the mean value has shifted towards a positive value, about 0.3. So that's an interesting finding to interpret these numbers 6.4. The baseline is not 0. The baseline is 0.3 or 0.4, dependent on the language. And that's an interesting hypothesis that was already discussed by social scientists in the 1960s. What's called the Pollyanna hypothesis. This hypothesis tells us that we use positively charged verbs more frequently. I mean, after all, it makes a lot of sense. No? Why are we talking to each other? We talk to also re-establish social bonds, and therefore it has a meaning that we also put some positive value into this language. But now we were able to quantify this Pollyanna hypothesis. That's the most important point here. The second measure of this physiological response, the second measure of this emotional content was the physiological response. On the right-hand side, you see a girl. It's a student from the Jacobs University in Bremen. So she was put in a nice box there, and then she had to chat and were basically monitored with respect to a number of physiological responses. Skin conductance, heart rate, also some muscles in her face, and so forth. And she had to look first into pictures, so-called IAPS pictures, that are normalized in the sense that we know what exactly is the emotional value associated with this little rabbit there or with the little baby over there. So that's our kind of baseline measurement that we do. And then this girl had to look into these pictures, and then we measured her physiological response, and afterwards she had to participate in an online conversation that we then also monitor. And then we have these two channels. One channel is her response, her physiological response, and the other channel is what she actually reads and writes. Okay. Here you see what we find when we look into the physiological data. The corrugator is a muscle that makes you frown. Yeah? So, this kind of thing. And you see how this goes down with increasing pleasure, of course. Yes? But this is the kind of curve we use to basically calibrate the physiological response. The zygomatic muscle is the one that makes you smile. So this goes up with pleasure. And the peak cardiac acceleration, which has to do with the heart rate and the blood pressure, this goes also up when we have positive emotions. So now we have quantified emotions in these two different ways. There's the physiological part. I will probably not talk more about this. And there is this language-related part, sentiment analysis, and so forth. How do we bring the two things together now? And this is in the model I was talking about. What we want to do now is we want to build an agent-based model where each agent is an individual. And we want to model the evolution of the emotion of any of these agents in our system. That's our aim. It's crystal clear from Russell's diagram how we have to quantify this agent along two dimensions, the valence and the arousal. Valence was the pleasure of the emotion, and arousal was the kind of activity that was associated with this. That means I have to write down two dynamic equations, how the valence and the arousal change over time. And this is written here in these two equations. So V dot is the time derivative, that means the change of the valence, and A dot is the change of the arousal. So you see three summands here on the right-hand side of the equation. Let us start to explain each of them. So the first one is a damping term here. It means if there is nothing that triggers your emotion, then your emotion shouldn't go up but go down, slowly but steadily. That's the assumption, right? So this term makes sure that we relax. This term at the end is a kind of stochastic term. Sometimes we get emotions out of the blue, right? And not just because we read some text. Therefore, there are stochastic influences that can start triggering some emotions. The middle part is the most important one. This is a function that shall describe for us how we respond emotionally when we read text from other people. And the same is then true also for the arousal, where we have to specify how the arousal changes dependent on the text that we read and so forth. I walk you now through some mathematical equations. It's not the issue that you have to understand this. The message here is we can fully formalize it. And I show you how this works. That's the issue here. The first step is we have to quantify our model with respect to the communication. So you see two levels here. One is the red level where we have the agent. The agent is described by the valence, that's the V, the arousal, that's the A, and the agent then at the end also has to type something, right? So that is S, the contribution or the expression that the agent at the end writes. This text that the agent writes goes into this blue layer, which is a communication layer. We describe it as a communication field. But the best thing is you think of this as of the screen of your laptop. You see all the information that's produced by other agents, and if there are more agents typing, then the older text goes further down the screen, right? You know this from every chat room. And you have to think of this communication field in a very similar way. It's constantly produced by all of the agents chatting, and it will decay over time if no one chats anymore, right? So that's the idea. What do we assume for these interaction functions? I don't go into all of the details, but if we have no clue of what we should assume, then we say, well, it should depend, the way I respond to these emotions should depend on two things. First of all, on what I read are the emotions of other people. This is this H. And secondly, it should depend on my emotion, right? If I'm in a very positive emotional state, I will respond to the same information differently as if I were in a sad state, right? So that's the assumption here, this BK times VK. And because I don't know up to which order, I simply write it down as this kind of power function here. For the arousal, we have a similar assumption. And then, at the end, we assume that the agent, if the arousal is above a certain threshold, then this agent simply writes something, and then the arousal goes down. That means the agent becomes a little bit more quiet, and then the dynamic may start again later when the agent reads other text that forces him in to write again. Okay. We could now discuss all these equations in detail. I'm not going to do this. I'm just telling you that there are arguments that we can already do at this level. Yeah? So I wrote down this summation over this B times V, right? So this looks like zero order, first order, second order, third order. I don't have any clue which of these orders play what role. I don't know what is B1, B2, B3. So these are things that we have to fit later on. But I can already tell a few things. Namely, if the B not is there, then the whole thing will probably not work, because with the B not, no one will relax with respect to his emotion. So B not is gone already. If the B not is gone, then we can argue about the B2, because we don't want to create a bias towards either positive or negative emotions. We can conclude that the B2 is also zero. So that means already on the level of the equations, we get some insights. One, what would be the regime where we get, for example, a observation of a high emotional response. So this is what we find. So below some certain parameters, we find a unimodal distribution that you see on the left-hand side, where all of the agents are more or less similar with respect to their emotion and rather quiet. But if the emotional information that is measured in this H, that was a communication field, has a supercritical value, then I see a polarization. I see that some agents in this model become very happy, whereas others become very sad. Of the same thing, different response to the emotions. So that means I can already observe a polarization in the emotional states just by looking into this model. For the arousal dynamics, I can do a similar discussion. The conclusion here is just that this parameter D2 plays a major role here. So if I find that the D2 is less than 0, then I see that there is one collective emotion in this model, and that's it. If for the D2 is larger than 0, then I see waves of emotions. Agents get excited, then the whole thing fades out, they get again excited, and so forth. That means if I talk about persistent collective emotion, this tells me something about the condition of this D2. Or if you want to put it the other way around, what we have here in our hands is a way to test different hypotheses. We can now argue about all of these terms. We can plug in what we want and then see whether the reality fits to what we have just discussed. This is the idea. We measure what is the impact of our assumptions here with respect to data. Here you see a few things, so I will be very short. So this is the number of agents that participate in this emotional discussion. I'm just talking about the computer simulation here. And then you see these waves of arousal here, that the agents become excited and they become less excited and so on. You see that the agents do not behave synchronous. So everyone is a little bit differently, but you see still these waves. Yeah? We look into the valence, and we see a similar behavior. We also see, if you look very closely here, that some of the agents change their emotions. That means their valence from positive to negative, but most of them go up and down. So this is all what we learn from the model. This pattern we have seen before, right? So our esteemed colleagues here, for example, analyze the mood of the nation. And there we also see oscillations. So is this the same thing that we just described with our agents? Not at all. The mood of the nation is triggered by a daily cycle, right? Good morning, America. Good night, America. These kind of things that were tweeted up to 1 million times, then of course, create a kind of collective mood, but this collective mood did not arise from the interaction of the agents. We want to have a model where your emotional response depends on my emotional writing, right? And not the other way around. So this is externally triggered. It's also an oscillation, but has nothing to do with the kind of phenomenon we want to describe. So what do we want to describe then? Let me start here with one example. Zurich as a capital of Switzerland. It was a Facebook discussion that then, of course, leads to nothing but raises a lot of emotions. So that's the kind of thing that you have to have in mind. We see then online discussions of people in chat rooms, for example. Let us look into Let us look into these kind of discussions. You see there's a timeline and users entering these chat rooms here. There's a user 1 who types something at T1, then user 2 also types something at T2, and so forth. So the different colors mean, do they write positive or negative or neutral comments there in this chat room? We can analyze this by means of the sentiment analysis, and we see how the other users respond to this. So it's like an open book to us where we can read what users write and we know their emotional response. So then the question is, what do we find in this data? We have analyzed 20 RSC chats, inter-relay channels. So this is a kind of discussion forum where topics are given by different channels, so 20 different topics. We analyzed the post of 20,000 unique users, and there was the whole number of posts was 2.5 million posts. So what do we see with respect to this data? The first interesting finding is this one here. That's the time at which a user writes the second time after he wrote the first time. Right? So I write something, what is the time lapse until I write the next time? So you see that I can predict the time that has to be spent before I write back the next time, follows this very clear power law, right? It's a log-log scale here. And this power law has a particular slope, 1.5. So that's a very nice finding. It means that the users in this chat room do not behave differently from other people on Earth, because this is a very prevalent communication pattern. People have analyzed the letters of Albert Einstein and of Charles Darwin. When Charles Darwin wrote the first letter, what was the time lapse that he wrote the second letter, and so forth. It follows the same distribution, for Albert Einstein. When I have mobile phone communication, it follows the same distribution. So what we see here is a very characteristic way of human communication. The other thing is also nice. It is this kind of stretched exponential distribution. You would argue, so what is the inter-event time here? It's a time that has elapsed between my post and the post of any other user, right? So, and then we find this kind of distribution here. Now we would argue, makes certainly a difference whether we talk about sports cars or abortion, right? So, of course, it makes a difference. In a heated discussion, people write faster. But if we scale this distribution by the average time, inter-event time, then we find this kind of pattern. That means users behave in these chat rooms in a very predictive way. That's a stretched exponential distribution. So this is the empirics. Now we want to take everything that we have learned and put it into an agent-based model that reproduces exactly what we have seen. So one step further, so when we look into this, there is another way of quantifying the users. So namely how persistent they are with their expressions. You would argue if I go to this anonymous chat room, then I would really write something bad. And, yeah, probably. Otherwise, why would I go to an anonymous chat room? What we find instead is that the users are very persistent with their emotional expression. So that is expressed in an exponent h here, capital H. So that is above 0.5. And we also find that they are on average more or less positive. Right? So that's an interesting finding. And this is what we want to reproduce. These are the results. I don't go into the details of the agent-based model. I already explained it. But here you see some of these features. We see the same kind of this distribution of the Hurst exponent that we have seen here. So that's the data that we see. And you just look into the distribution of the persistence of the users. And this is exactly what we see here again. We also can reproduce the time it takes after someone has written something and the next one has written something. That was this inter-event time, the stretched exponential. You see, this is exactly in line with the empirical findings that we have found. And this really tells us a message about the validity of our modeling framework, if we are able to reproduce this. But we have done more tests like this, so let me just talk about the product review issue. So I can be very short here on this. So this slide is maybe good for Andreas because it tells us that ratings have nothing to do with the expressed emotions. So we see here that the ratings and Amazon reviews are always very positive, but the emotion expressed in the text that people write, so this spans all scales here. Okay? So we looked into the dynamics of these ratings like this here. This is the number of reviews people wrote over time for a particular product. This was Harry Potter and the Deathly Hallows. And there was another product which was not as famous as Harry Potter, but propagated through a word-of-mouth effect. And now we find the following that if we look into the emotional expression that people wrote about these products in their reviews, there are thousands of reviews for these products, so then we see that such a characteristic picture appears here. As you see here, there is a negative part, and then there is a strongly biased positive part that we see for Harry Potter. We see the same thing for Twilight New Moon that was propagated by a word-of-mouth propaganda, right? So that's an interesting pattern for those people who spend millions of marketing budget to make Harry Potter a very famous and important book. It does not affect, at least, the emotional response of the users. So that's one lesson. And then, this is our simulation, and I just want you to look into the picture on the right corner. And here you see what we have gotten from the simulation of our agents. The same kind of response with respect to the emotional frequency of the valence. And that's the negative and the positive score. That means from our agent-based model, we are able to reproduce characteristic features of what we see in these data. That's a message. Let me come to my conclusion slide here. I skip all this, and that's the conclusion slide. I followed closely the discussion of today, and I found it very remarkable that most or many of the discussions related to computation and social science focus on the engineering aspect. That's the aspect of statistical regularities. What's the correlation between feature X and feature Y, right? We can do this as we have seen today. What I find much more important is to make computational social science a science. That means that we have to address these issues, not only what do we find, but also why do we find. In particular, what we want to understand, and that's why we also built this model and are not satisfied with the fact that we can simply find something interesting in the data. We want to understand how agents influence each other by means of these social online media. And this is what we wanted to capture in our agent-based simulation. And I hope that the example that I have shown can also convince you that we achieved this kind of goal. For us, the issue is important. What does it mean to be a human in an online world? And how much do we differ from being humans in the offline world with respect to these characteristic features? And the conclusion that we found is we differ not too much. Thank you very much.
Thank you very much for your very nice talk, and also for the very nice last slide, which sort of reflects on many of the things that we've heard today. We now have time for one or two more questions. Any questions? Yes.
Thank you very much, especially for pointing at in my point of view, the pressing questions here. I have two questions. One is about your theoretical model, where you have the deterministic part and the random part.
Yes.
Do you have a problem with identifying the parameter when you have a chaotic behavior solely because of the deterministic part when you add a random part? And the other one is for your application, where you have the IRC chat protocol. I guess you have thought about it, but if you tried this as an experimental lab where you add impulses into the chat history.
Okay, good. Two interesting questions. The first one, you can relax, so we don't see any chaotic behavior in online human behavior. We don't see any chaotic behavior. The chaotic behavior is a very well-defined issue that we learn, for example, from deterministic chaos. But this doesn't happen in what we see here. We see, of course, a lot of randomness in the signals, but this can be well distinguished from chaotic behavior. So that means the deterministic part, at least for the examples we have looked at, is never chaotic. And the random part can be approximated by means of data analysis. So there is a firm way to distinguish the random and the deterministic part. The tricky thing is, so if to point to this, is our agents are heterogeneous agents. They are not the same. So in order to find out what's the variability, for example, for the random part, that's a very hard issue. Yeah? So there we have to use a number of subtle considerations. For the second question, this is also interesting. This brings me to this thing, well, what can we do with this? In fact, so we did experiments like this. We have put emotional chatbots into this discussion. So people had to agree to this, according to the regulation of the European Commission. So you had to agree that there are chatbots in their chat. And then at the end, when they were about to log out, they saw a screen. Did you notice the chatbot in your chat? And they could answer yes or no. So the majority of the people answered no. Right? So that means there is a way to computationally construct these chatbots so that they can mitigate heated emotional discussion, for example, without the users notifying that this is a piece of software instead of a human moderator, for example. So that's something that is already underway, yes.
Which brings us back to the engineering aspect that
yes.
you just raised, right?
Yes.
Can you engineer conversations such that, for example, they take place in a certain civil kind of spectrum that one would desire? That would probably be a practical implication of what you just described.
But that's not my question, I have to say. So my question is a scientific question. I want to understand how, for example, humans respond to certain kind of incentives that we generate in every direction. So what you then do with this in an engineering context, that's a different thing. So, but we are not actively developing these kind of things. However, sometimes I think it's very good to have ways to mitigate discussion for example, particularly if you look into the comments section of certain newspapers. Yes, that is already a feature by itself, to see how people express themselves there, and just to have a little tool that first of all monitors this, and secondly also tries to mitigate it, would be not really bad, I would argue.
Okay. Are there any further questions? If that's not the case, then I'd like to thank our speaker once again.